Hey everybody, in the last video we talked about polynomials, and now we're going to talk about a specific type of polynomial called quadratics. Okay, so in lesson 7.1 you were introduced to polynomial functions, including second degree polynomial functions, which we call quadratics. Right? The general form of a quadratic we saw before was y equals ax squared plus bx plus c. In this lesson, we're going to work with two additional equivalent forms of quadratic functions. So we're going to be able to write different types of equations based on the information that we have. This is useful if you just know a and b and c. You can plug this equation in. If we know some other things, then we can probably plug some other values in, and we can probably get an equation that is still a quadratic, but it might be easier to write it in that way versus this way because of the information that we have. Okay, so we're going to look at this Desmos graph real quick, and what I did was I have the graph over here, ax squared plus bx plus c. I just put in some values, and this is my graph. Now, if you remember from before when we were talking about transformations, we know that usually parabolas, the parent function, goes up, and now it's going down. So we can say that we know it's a reflection over the x-axis, right? Because it was opening up, now it's opening down, and then it normally would be at 0, 0. It shifted to the right and up. Well, how many to the right and how many up did it go? It went that many. So if we wanted to write this, we could say our equation could be y equals, and normally it would be x squared, x, and then we had this as we went to the right, 0.75, so minus 0.75 squared, and then it went up. How many did it go up? It went up 1.563. So plus 1.563. Okay, so there's our equation for that. We just say, and now we know that there has to be a negative out in front. And I'm going to tell you that this isn't such a great graph to look at, but we can always do is so go down one, go right one, or down one and left one. And if that's in the same spot, then we are going to know if we go down one and right one, and that's on the graph, down one and left one, it's on the graph, then we know there hasn't been any sort of vertical stretch or shrink or horizontal stretch or shrink. So we know there's just going to be a negative out in front for the shift over the, or the reflection over the x-axis. So this would be our new equation. Okay, and this new form, y equals a x minus h squared plus k, is called vertex form of a quadratic function because it identifies the vertex. We know where this one point is, the top point of this graph, which is really kind of an important thing about graphs, especially if you think about projectile motion, things flying into the air and coming back down. We might want to know how high does it go before it starts coming back down. So that would be an important point. Okay, it identifies the vertex, h and k, inside and outside, right? How much did it shift left or right? How many shift up or down? In a single vertical scale factor, a. So this a could be positive, it could be negative, it could be 1, it could be 9, whatever. If you know the vertex of a parabola and one other point, you can write the quadratic function in its vertex form. Okay, so vertex form is really going to be quite handy. Okay, next, the coordinate of any point along the x-axis is 0. So maybe before we go on, we should just go back and check. This new form, vertex form, is one of the two forms that is really important. Okay, vertex form. So right now we got general form. We have y equals ax squared plus bx plus c. That is one form that we have. We know a and b and c, just it's the general form. If you know the vertex, then this would be a pretty easy equation to write. If we knew what the vertex was, we know these two things. If we know one other point, we can figure out what that a value is. All right, so these two are similar equations, and if we would have the right values, we could have them be the exact same graph, just different looking equations. And the nice thing is this a value right here is the same as that a value right there. So if you know it for general form, you know it for vertex form. Okay, so those are our two forms right now. So we can say quadratic forms. Okay, and if you remember in the little intro that we did, there is another form. Okay, so besides knowing the vertex, there are some other important parts on the graph, and there's really only two more, and that would be this point and this point. These 2 points where it crosses the x-axis are going to be two other important points. And if you think about projectile motion, things flying through the air, not only do we want to know how high it goes, but we want to know when is it going to hit the ground again. Okay? So let's talk about that kind of stuff right here. So the coordinate of any point along the x-axis is, the y-coordinate along any point of the x-axis is 0. So we can call the y-coordinate 0 at each x-intercept, right? So the x-intercept, notice, is when the y-coordinate is 0. For this reason, the x-intercepts of a graph of a function are also called the zeros of that function, okay, because it crosses the x-intercepts. The zeros because the y value is 0. If you notice here, the y value is 0 on this one, the y value is 0 for here. You will use this information and the zero product property to find the zeros of a function without graphing, okay? So, for the real numbers a and b, if a times b equals 0, then a is 0 or b is 0, or they're both 0. This is something that we've done before a lot. We try to set equations equal to 0 and then say, either this one's 0, that one's 0, and then we can solve. Okay, we kind of like, some things we've done with absolute value are kind of similar to this idea, but we know if we multiply two things to 0, the only way to get there is if one or both of them are 0. Okay, so there we go. There's the zero product property. Let's do this example. So this example says find the zeros of the function, this whole thing. Okay, so the zeros, again, we say are when the y value is 0. So what I can do is I can plug in 0 in for y and get negative 1.4, x minus 5.6, x plus 3.1. And we can say, in order for this to be the case, when I multiply three things together to be 0, either this one equals 0, this one equals 0, or that one equals 0. So I can say, does 0 equal negative 1.4? Does 0 equal x minus 5.6? Or does 0 equal x plus 3.1? Okay, so for the first one, we know there's no solution. That's not going to happen, right? For the next one, if we just add 5.6, we can say 5.6 equals x, so that one is solved. And the last one, if I subtract 3.1 from both sides, I get negative 3.1 equals x. So if it says find the zeros are going to be x equals 5.6 equals, and x equals negative 3.1. If we want to find the zeros and it's in this form, man, is that really easy, right? So there is our solution for that example. Now, if you know the x-intercepts of a parabola, you can write the quadratic function in factored form. Y equals a, x minus r1, r2. And this form identifies the location of the x-intercepts. We're calling them r1 and r2. We call them r because, remember, one of the ways we can say what they are called is they are the roots. So r1 and r2, we have two roots and a vertical scale factor of a. Okay, so there is our next form that we have. So if we just go back and find that other form that we wrote some stuff down on before. So we have quadratic form. We have this one as general form. We have this one. Do you remember what this one is called? That's right. It's called vertex form. And the last one is called intercept form. An intercept form is going to be y equals a, x minus r1, x minus r2. Okay, and again, this a value is the exact same a value as all of those. So for this one right here, we can say, not x, I don't want to do that, I want to do h comma k is the vertex. And then for this one, we can say that r1, r2 are the roots. Okay, so we have all three forms. It depends on what information I have and what information I want to find out. Depends on which equation I want to use. Okay, so let's just go through and see if we can do this last example real quick here. It's going to be this one right here. We're going to write the equation of the parabola in vertex form, in factored form, and then show their equivalent by converting them both to general form. So we're going to look at this one right here. Okay, so we're going to try and see if we can get these values to come out when we go through and actually solve this parabola equation. Right? So we're going to write the equations. We're going to see if we can get them to look like this one right here. Okay, so first I'm going to go to vertex form. Oops, I want this right here. We're going to go vertex form. So again, the vertex form is going to be y equals, I know it's negative 1 x minus h squared plus k. So if we go to this graph, we're going to say x minus 0.75, 1.563. 0.75, and I need to get rid of this. 1.573, right? I think it's 1.563. 1.563, okay. So then what I want to do is I want to expand this out, and this is a negative right here, and we should be able to get that in the other form. But now what we're going to do for now is we are just going to go to do intercept form. I'm sorry, intercept form, aka factored form. They're kind of synonymous, they're the same thing. I'll go back and change that over here too. And I said intercept form, we could also call this factored form. They're kind of the same thing, okay? So this is just a different way of writing the same thing. So if I say intercept form, I say factored form, you know what the heck I mean. Okay, now let's go through and write this in factored form. So do we know on this graph what the zeros are? Well, negative 0.5 and 2. So I can say y equals negative 1, right, because that's my a value, x minus negative 0.5, negative 0.5, and x minus 2. And there it is in factored form. So now what I should be able to do is I should be able to go through and convert both these to general form. So this would be really part A. This one's part B. And now if we want to try and convert them, we can do that. Okay, so that means I have to try and do x minus 0.75. So if we think about the box method, x negative 0.75 and x negative 0.75. Okay, so we have x squared negative 0.75 x negative 0.75 x, and 0.75 squared, let's just do that, 0.75 squared, I get 0.5625. Okay, so this is 0.5625. So I get x squared minus 1.5x plus, and we said that was 0.5625, 0.5625. So that was this whole thing right here, went to here, and that's this, and then we can bring this one down right here and say 1.563. So if we add that to plus 1.563, we end up with 2.125. Sorry, hold on. Before we do that, this whole thing is still a negative. So it means I have to put the negative in front, which means I can get y equals negative x squared plus 1.5x minus 0.5625 plus 1.563. And I'm thinking that Desmos here, when it had this point, it rounded it to just three numbers after the decimal point. So if I have this one a negative and this one is a positive, this number is going to be the same as this one. It just doesn't, this should be 2.5 right here, okay? So it means I'll end up with y equals negative x squared plus 1.5x plus 1. Okay, and now we have to do the same thing for this one right here. So we have y equals negative 1, x plus 0.5, x minus 2. Okay, so y equals, and we can just kind of do the same box method, x times x is x squared, so we get negative 1x squared. X times negative 2 is negative 2x plus 0.5x, and then minus 1. Okay, so we get y equals, and I'm just going to do all this at one time, negative x squared minus 2.5, or minus 2 plus 1.5 is negative 1.5 times negative 1 is plus 1.5x, and negative 1 times negative 1 is positive 1. So we end up with this one, which is the same as this one, which is the same as A, B, and C. So there you go. We just showed that these are equivalent expressions, equivalent equations, and they are both in general form. All right, so there you go. Good luck.